Okay, maybe can everyone give maybe like a thumbs up emoticon or something if you can hear me and see me and also see the slides? I guess that was 3 questions and only 1 thumb. Sorry about that. All good. Okay, great. My name's Thomas, same guy who gave you the recorded lectures. So just for today, what we'll be doing, hopefully you've already watched the FixedWing like pre-recorded lectures, the 3 different video segments. And so this morning for the next hour, I guess you see on the screen here. So we'll go over just basically the outline of what you'd need to know from the FixedWing part of the lecture for the exam, a brief review of some select topics. I thought maybe it would be good to go back through a bit more in detail. We'll go through 1 practice exam question, and then at the end we can also have maybe some questions if you guys have more than what was already on the piazza. Okay, so let's make sure this slide works here. The laser pointer. You can all see the laser pointer as well. Maybe another thumbs up. No thumbs up, or at least I don't see me. Okay, well anyway, hopefully the laser pointer is showing. So maybe let's just quickly go through the outline for what to know for the exam from the lecture. So first thing, probably one of the most important, is what are the aerodynamic forces and moments? So the names, lift, drag, pitching moment, yawing moment, all of these that were in the last lecture, they're very important. But then also, so the definition, so basically dynamic pressure times surface area times the lift coefficient for lift. What is dynamic pressure? So this would be, it's also in the equations from the last slide. So we'll see in a couple slides down, you'll see this equation again, so I won't go more over it here in the outline, but just generally. So aerodynamic forces, moments, very important. So please know those and their definitions, where they're defined. Second thing is flow characteristics. So another important one would be, what is stall? So again, like what point does stall happen at? What is the actual definition? And what does it do to the aircraft? Another thing for flow characteristics, so we'll go over these in particular actually in the next slide, or in 2 slides from now. So laminar versus turbulent versus separated flow. So I actually chose these as one of the selected topics for today to go over in detail, because they can be a bit confusing, which one means what and do they overlap at all. So we'll get to that in a couple slides. So then finally the airflow angles, so angle of attack, side slip, these definitions you should know, especially the angle of attack. That's one that we'll use in the practice exam question as well. So then the 4 main control surfaces and their functions. So that was the rudder, the elevator, the ailerons, and maybe, oh yeah, and I guess it's not a control surface, but the throttle would be your other control input that we used in the lecture. Or you could maybe count 2 ailerons as 2 different surfaces. But those are the main ones. As you saw in the slides from last week, or on the pre-recorded lectures, there's tons of other things like flaps, spoilers, air brakes. We don't need to know these for the lecture, but if you can look at them more in detail if you're interested. But 4 main ones that just generate our main moments are what are important. Also knowing, I guess, what kind of moment they engage. So if you have the elevator, for example, on the horizontal tail, you would need to know that it gives you a pitching moment. That's the main reason we have that control surface. And then so on for the rest of them. So then frame definitions are important. So fixed wing has a few different kind of strange frames compared to the multicopters, like the wind frame. So just make sure you review the slides and kind of know how those are all defined. Coordinated turn is another important topic. So that's, again, we'll go over this in the practice exam question here in a few slides. That also involves minimum turn radius. It's an easy thing to calculate once you know the definition of the coordinated turn. And then finally, just generally speaking, so I mentioned in the pre-recorded lectures on the guidance and control, so you don't need to know, for example, the derivation of the total energy control system, high-level controller, or the L1 guidance controller, but just generally know what is that cascaded guidance and low-level aircraft control concept. So the one we described in the video segments from last week. Basically having the high level taken care of, position control, giving airspeed and, controlling airspeed as well. So altitude and airspeed, for example, on the longitudinal axis, lateral position control on the lateral axis. These then giving those attitude references to our low level attitude controller. So again, those are in the previous slides, so I won't cover those too much today. But let's get then to the flow characteristics. So this is one of the ones I wanted to really cover in a bit more detail. So laminar flow. So I remember in the first video segment that was pre-recorded, I talked a lot about streamlines. And so streamlines are basically assuming some kind of laminar flow. So we're the particles following a very smooth path. It's not really getting disturbed by other particles too much. It's nice flow, I guess is what you call it. Turbulent flow, on the other hand, it's when it gets a bit more chaotic. So there are reasons for why it becomes chaotic. This is something you can learn in an aerodynamics class. For now, we'll just know that this is the more chaotic flow. So you see it here, kind of when it blows up a bit, this boundary layer. So this means that the pressure and velocity is actually quite rapidly changing, bouncing around. So now getting to this separated flow. So separated flow means we actually down here have reversed the direction of the flow a bit. That's where these vortices are forming. So literally the flow is spinning around here like a little cyclones, or eddies is what they're called, these vortices. So the flow has actually turned around next to the surface here. That's what these rotations come from. But the thing I wanted to really point out is that turbulent and laminar boundary layers, they can both separate from the surface. So claiming, for example, that if my flow is turbulent, that it's automatically separated, this is not true. So you can have a attached turbulent boundary layer, just like shown here, and also a laminar one that's attached. You can also have detached laminar and turbulent layers. So there are two separate concepts here, turbulence and laminar. These are just, I guess it stops the little animation, but so these are just describing the properties of the flow, the characteristics of it, but separation literally means it's actually come off of the surface and cause these vortices. So actually, why is it now not? There we go. So then the last thing here, and this is related to separated flow, so stall. So the definition of stall is that we have started to have flow separation. And so then the whole thing about stall causes this large reduction in lift. This is actually because, again, of the separated flow. So a turbulent boundary layer may have, it actually really depends on a lot of other factors. So I don't think you can really say a turbulent boundary layer versus a laminar boundary layer will have more or less lift. It'll depend on the flow speed, the angle of attack, different things like this, the geometry. But you can say for sure that once that boundary layer has separated, you definitely will have a reduction in lift. So again, coming back to the turbulent flow and it being attached and it's still generating lift, I can give an example that actually even commercial jetliners will have specific little bumps along the wing that are actively trying to generate turbulence. They actually want the turbulence over the wing. And the reason is that turbulent flow is a bit more energized and actually can stay attached longer at higher angles of attack. So this can delay separated flow, basically. You're trying to stay attached longer. So you can go to higher angle of attack before you reach the unsafe stall condition. Turbulent flow, however, will probably increase your drag a bit. So it's kind of a trade-off. If you want to make a turbulent layer instead of a laminar layer, you will get a bit more drag induced over the wing. So that's all I'll probably say about, oh, I see a question here. Does stall refer to a point of position where the separates? Oh, this is a good question, actually. So thank you, Chin Hao Li, for the question. Basically, so I only put here that once the flow separates, we call it stall. But it's actually kind of a bit more of a continuous definition. So let's say on this picture, you see that there's only a little bit of the tail or the trailing edge that's actually separated. So we would still say that once any amount of the flow is separated, we have entered the stall regime. But you could also say something like we're more or less stalled, like if more or less of the top surface here is completely detached or partially attached flow. So also depending on the geometry of the airfoil, they actually design these to have different stall characteristics. You could have a very sharp stall. So for example, very thin airfoils would often have kind of the curve would look really sharp. It'd drop off really fast with the separated flow. So it'll go from no separation to almost full separation faster than, let's say, a kind of wide, thick airfoil. This is not a general rule. This is just most of the time happens. Again, airfoil geometry is quite complicated, but different designs can cause different kinds of stall behavior. So you could have a very smooth stall behavior with your lift versus alpha curve, or you could have a steep drop off. But for our purposes, we'll really consider that once that stall point hits, we're expecting some kind of pretty large reduction in lift. And this is typical for most airfoils. Okay, so again, actually that's maybe that's something to mention. So as we're going through some of this, if you want in the chat to just put some questions, like maybe I missed something as I'm going through or something wasn't very clear, please feel free to put some questions in the chat and I'll try to pay attention to the chat as I'm going through. Okay, so now let's actually get then to practice exam questions. So this is something like what you might actually see on the exam. So on the right here, this is a table that actually corresponds to these two identified static lift and drag curves for the TechPod UAV. So this guy here, we actually went outside, did some kind of gliding maneuvers, different pitch angles, different angles of attack, different airspeeds. And that's what all these gray data points are. So this is from real flight data, plot all the points, and then try to fit a curve through it. That's basically all that's happening. So from these fitted curves, then we have the table, and then here's some geometry for and characteristics of the plane. So S, remember, is surface area. So that's the wing plan form area. From the other video segments, remember this is looking top view down at the wings. So we're not considering how the wing curves at all. This is just top view, look at it, and you can calculate the surface area. And this is 0.4 meters squared, specifically for TechPod. So then we have a mass and the gravity, because we're not going to space, so we just keep 9.81, and then this is sea level density. So another thing here. So I'm glad I always remind myself with red boxes what to talk about. So we're also assuming in this exam question that lift and drag coefficients, they only depend on angle of attack. So basically what you see here with this red curve, oh, my screen went to sleep. I don't think so. I still see it. Is this happening for everyone else?
No, we can see also.
It's okay?
Yeah.
Okay, great, thanks. Okay, so then back to the lift drag thing. So Angle of attack here on the x-axis, lift, drag on the y-axis. So this red curve is all we're considering for the lift and drag coefficient. Moving on through the question. Okay, so next then, so this is then the first part here. So the TechBot UAV, we're flying straight and level. And remember, these definitions you can find in the last video segments at cruise. So then somewhere around 11.5 meters per second. So then, first thing, what roll angle produces the minimum achievable turn radius at the current speed? And we're assuming a coordinated turn. So to remember from the last slides, we had a little figure like this. So the main thing here is that if we have a coordinated turn, and we said we're level, so we're staying at one altitude. We also said specifically in the last question here, or in the question here, that we have a defined airspeed. So this airspeed shouldn't change. So with all these assumptions, the only way we can maintain that altitude, compensate gravity down here, and try to get the minimum achievable turn radius. So turn radius then would be determined by how much, yeah. So basically the maximum centripetal force we can apply here will give us our minimum turn radius. So how do we generate that maximum centripetal force? The only thing we can do here while still compensating gravity then is basically roll and increase this lift vector at the same time. So our lift force as we roll to compensate gravity still needs to get bigger. So we need to increase our lift. But then as we do that, we increase this centripetal force. So then if we look closer at this lift equation, so these are the equations that you'll need to remember for the exam, also for drag moment. And so here we remember that our lift coefficient per the problem is only defined by alpha, or a function of alpha. But then we also have our speed here, so density, surface area. So then if we look, what can we actually change to modulate the lift here? So we could change our speed, but we already know we're keeping one speed. So then the only other thing that's not constant is our lift coefficient. So then the question is, now how do we find the lift coefficient, which will give us our maximum centripetal force, which in this case then means our maximum lift. So we want to maximize CL. So let's go back to the table. And if we look down here, we can just look at our CL values actually. And the highest ones here at 10 degrees angle of attack. I think, yes, I highlighted. So, and if you remember also from the stall definition in the last video segments, or in the pre-recorded lecture, so stall will also occur then at CL max, so our maximum lift value. So that's just another kind of thing to remember. We'll get back to that in a second, actually. So then we have our CL max now. And so writing out the force balance here. So we have lift of CL max times cosine of roll needs to equal our gravity. So plug everything in. And then we can pretty quickly solve for this roll angle. So that's the roll angle at which our maximum, or our maximum turn, or minimum turn radius, sorry, will happen. So then continuing with the force balance. So we also need to make sure then that, or then like let's say to figure out what the radius is. So we have our centripetal force here, and then lift times the sine. So our horizontal component. If we divide the equations through and then rearrange, we get down to our turn radius here. So this is the minimum turn radius given this roll angle here and the maximum lift that we can achieve. So this is what would be expected on the exam. Basically, please always on the exam show your work. The numbers are not as important to me as the process. So you should know what the force balance looks like. So these equations written out, here's the force balance, here's how you rearrange it. And then, you know, because for example, if you type into your calculator and maybe you type a wrong number by accident, if the only thing you show at the end is this number and it's wrong, then I have nothing to give, you know, partial points for. So if, it's really important to show the equation in the exam. That's really the more important part. And yeah, so then let's see, I think there was a question down here. Lift is perpendicular to the flow, so perpendicular to VA. So how do you understand the direction of L? What if in case of wind? Direction of L. So probably, okay, I'm guessing what you mean by this question. So again, I'll repeat the question for everyone. So in the chat here we have, so if lift is perpendicular to the flow, so perpendicular to that airspeed vector, then how do you understand the direction of lift? And then what if in the case of wind? So I'll try to maybe do two parts of an answer to this question. So maybe I'm hoping this is what you mean by this question. So we know that the airspeed vector, or actually, okay, so maybe I'll just, I'm not sure exactly what you're asking, but I'll hope to answer it in this question. So basically the airspeed vector we're assuming is still moving directly forward, right? So coming in this last slide here, directly out of the page or out of the slide, out of the screen, I guess in the computer case here. And so lift is still going to be perpendicular, so it's flat on the page now. Of course, so then if we increase angle of attack, we're shifting the body axis more and more and more up. So the body axis isn't any longer pointing directly out of the screen, but our airspeed vector is. So the lift is still perpendicular and lying in this screen plane. So it won't change with the angle of attack here. So we can still say this guy is directly lying on the screen plane. In wind, as we've defined wind in this lecture, so we're only considering steady, constant wind. So no transient effects, no force effects on the plane, only basically once it's settled and we have a velocity component for wind in the inertial frame. So since we've defined wind in this way, where it's only in the inertial frame and it has just a velocity component that's added to our airspeed to get ground speed, this won't change the lift vector either, because wind is defined as the whole air mass's movement. So since we're flying with our plane around in the air mass, our lift is only, basically the lift's only modulated by that air speed, so the air mass relative motion. So I hope that answered the question from a collage.
Yeah, actually, my question was about the direction, right? So I know that it has to be perpendicular to VA, right?
Mm-hmm.
And VA is the velocity that the airplane has with respect to the what we call wind or the air, right?
Sure.
And if it's so, I mean, if I have wind, we saw that in the slides we change VA in the body frame because we represent VA in the I frame, and then we add the wind component. So I was supposing this, that VA changed direction clearly. And so since it changes direction, also the direction of the lift could change, right? Could change.
So sorry, how, okay, so if you're saying if airspeed changes direction, then lift changes direction. I mean, it will follow perpendicularly, right? So basically that wind frame diagram from the last lecture, maybe, I don't know, I have to share another screen to show this. So the slip will, so basically slip and angle of attack are the only kind of rotations you go through to get to that perpendicular vector. I'm not really sure what the question is.
Okay, it's fine. I will write on Piazza probably.
Okay,
Yeah,
sure,
yeah,
thank you. Yeah, sorry. But yeah, so please, if I'm having troubles understanding a question here today, please don't be afraid to put on Piazza, and then I'll take a look later for anybody else as well. Okay, so then let's maybe move on. So what did we do? We did part A here. So now we've already gotten to our, yes, minimum turning radius with all these assumptions. So then part B, and this is, I think Marco will probably give out some practice exams at some point before the exam. This is probably a question you will see on the FixedWing part in every single practice exam, at least in some form or not, is this a safe flight condition, and why or why not? So let's answer the question. So is flying at CL max right at the stall point safe? I would say not. So basically when we're flying around, there's lots of little, gusts that can happen. Our plane is not perfect. The controller for the autopilot's not perfect at stabilizing an exact angle. So if we're really right at the start of stall, and maybe we roll a bit more, or we have a small gust that pushes us slower or faster, we can stall, and then we run into issues. So in general, you really shouldn't design your flight speed or your flight condition right at the stall point, CL max. So that's all this question, this part B really wants to know is it safe? So if it's right next to stall, no, it's not safe. And then the why or why not for the exam as well, remember to please answer this question, why or why not. A lot of times I'll see answers to something like this, like yes or no. It's not going to get full points. I want to know why. Okay, so then moving on, this is part B then of the practice exam question. So we're considering the same plane, same lift and drag table, and same airspeed. So then now we're going to consider some headwind. So this is 3.5 meters per second. So if we look at headwind, that means he's actually coming down in the opposite direction that we're flying, which means then our ground speed gets reduced here by the wind. So then let's say we're still flying on this radius. So part A, is it possible to achieve the previous minimum turn radius relative to the ground? So this is a typical thing we actually want to do when we're flying. So if you tell the plane, please fly in this circle scanning over this field, you actually want it to, normally you're trying to measure something directly over the ground. So the ground relative position is more important than the air relative. So once again, is it possible to achieve previous minimum radius relative to the ground while keeping the same airspeed? So again, here's just our magnitude definition of the ground speed. So I mentioned earlier, so make sure not to be confused here. I said that ground speed was airspeed plus wind speed. And this is true in the vector form. So here you see airspeed vector plus wind speed vector gives us our ground speed vector. Here I'm just showing that in this particular case of headwind, you can write the magnitudes out like this. So just to avoid confusion there. So now we know what our magnitude of the ground speed is. And basically we'll need to find, so a new roll angle. So we can plug to the same equation we had before, except this time now we're using ground speed as the speed, not the airspeed. And so we get actually here, you notice a smaller roll angle. And then if we rearrange the lift equation, so then with our new roll angle, so smaller roll angle, we see that our angle of attack is reduced. So we keep the airspeed the same, have a new roll angle that's less, and now we have a smaller angle of attack. So this is angle type of 4. The other thing that'll happen on the exam with this kind of table is that we'll just take the closest value. So I don't want anybody wasting time trying to interpolate or something. Just closest value. The problem should be designed in such a way that it's quite close to whatever a value might be here. So here we have 0.902, 0.904 is pretty close. So now we have new roll angle and lift coefficient. And then Mike's saying, yes, this is a good question. I was going to get to it, but I'll answer it now. So Mike says, as the plane turns, won't it fly out of the headwind direction? Totally true. So this is actually, I hope I wrote it actually in the question. If I didn't, I'll edit the slides. So I wrote this particular point here, in this instant. So the only way we can consider this problem as we are is that we're saying, in this instant, can we achieve that curvature? And so as soon as we integrate our vehicle, one step forward, of course, now the conditions change. So our ground speed will be slightly different, and we'll need to have a different roll angle. So this is actually something that happens for, it's important for guidance logic, for example. So like the L1 controller, you'll see in the exercise next week that it uses the ground speed as its feedback term. And the reason it does this is exactly this whole point, that we're only considering in this instant on this curve what roll angle we need to achieve this curvature with current ground speed. But Mike's totally right that as we continue on this curve, our ground speed's changing, and so we'll need different roll angles for every single point on that that loiter radius. So back here, we had our new, yes, roll and lift. So yeah, back to then the question, is it possible? So yes, it's possible because our roll is not, anything absurd. 24 degrees is fine. And our lift is still within our range that we can safely fly at. So the other thing, so on the exam questions, I try to be as precise as possible about what I'm asking for, but remember that, so something that says like, is it possible to achieve a minimum turn radius while keeping the same cruise airspeed? Again, if you answer something like yes or no with no work shown, it's not, the point is not to say yes or no guessing 50-50. The point is to show the work and know the process. So if you don't show the process here with the equations, you won't get the points. So just know that when you go into the exam, that unless it's, let's say, particularly asking for just a yes or no answer, normally you need to show the equations. But it'll only be really out of these few equations. So then let's move down to part B. So once again, the same question that'll probably, I would, yeah, I think it's a good bet to assume that this question will be on your exam somewhere. The flight condition, is it safe? So back to this part B, is it safe? And probably you already know the answer. So our stall angle and our CL max is down here at the dotted line. So then we already saw here that we reduced our angle of attack to 4 degrees, which is far below stall, so we're safe. It's totally okay. If we were at 9 degrees or something, you could argue, okay, if I have the best autopilot ever, maybe I have 1 degree precision for flight controls, I would doubt it. So if it was something like 9 degrees, you'd probably still say it's not that safe. But 8, 7, 6, you're getting safer and safer. So on the exam for this kind of question, is the new flight condition safe? This is about all I would be expecting to see. So something like, it is far below stall, so it's safe. If it ends up being something close, like 9 degrees, you can just write, an extra sentence, basically say, yeah, it's really close to stall, so it's probably not that safe, but we're not stalled yet. You can say something like this. But that's all I'm really looking for. I just want to know that you understand what is stall, where does it happen, how do we get, different turning radii, how do lift and roll and speed interact, how does the wind act on the plane in the inertial sense. So these are just the general concepts that you can expect in an exam question. So then a couple new questions here. So let's see. So stall is where CL is maximum or 15. That's in slides. So I think I actually put a box to just, or like a note on that particular slide about the 15 degrees that stall happens in that particular figure. So I I put the note because it's been confused in the last years as well. So there's not a particular angle that the vehicles stall at. It depends on the geometry of the wing, the plane. So 15 degrees is not always stall. So here, for example, 15 degrees is far beyond stall. 10 degrees is stall. So yeah, in the slide from the lectures where it was just showing an example of different angles of attack and what stall kind of looks like when the flow starts to separate. So this, please remember in that slide from the pre-recorded lectures that there is no set number for stall. It's very dependent on the plane. So it can happen, I'd say normally it happens somewhere between 9 to 15-ish. If you have a better airfoil, maybe you can get up to 20, but that's quite high. Really, it's normally around like somewhere between 9 and 15 degrees is for most planes what stall will happen in. Okay, so then another question here. What if the angle of attack is larger than 10? Yes, so if the angle of attack is larger than 10, so in this case, since 10 is our stall point for the tech pod, then we're still stalled. So we're just getting more and more. So I kind of talked about that continuum earlier, that we're basically separating our flow more and more and more over the surface of the wing. So we're getting worse and worse and worse. So the lift drop off is just going to keep going down in this case. If you get into kind of crazier flight, which we don't cover in this lecture, actually it's possible in the case studies next week. So we're doing some hybrid platforms in the case studies where actually these post-stall states become a bit more important. Maybe, I haven't seen the slides yet, so maybe David and Mike will, or Sebastian will show you what this post-stall curve looks like. So all the way to like 90 degrees angle of attack, for example. For regular fixed wing planes in cruise flight, we definitely don't want to go past the stall point, but if you were to go all the way past the stall point, so far beyond 15 degrees, for example, here, at some point the drop off kind of rounds out, and there's a condition called deep stall. So if you're interested in deep stall, it's actually pretty cool. You can look up, I don't know, go to YouTube, type in deep stall. Maybe you'll see some RC pilots doing an example of it. But basically your flow is almost totally separated on the wings, but you enter a condition where you can actually stabilize as long as you have a full moving horizontal tail that can regulate your pitch. So the full moving part of the horizontal tail is important, because then as your airspeed vector is pointing basically down in this deep stalled condition, you need to be able to also point down such that your tail is not stalled. So your wings are stalled, you're losing all this lift, you're creating a bunch of drag, all this separated flow, but you can stabilize that condition with that tail that's actually in the flow, so it's not stalled. So that's a bit more advanced stuff. It's not something you need to know for the lecture, but just if you're interested, it's kind of cool. So then, okay, next question here. What is CL above stall? I'm not sure what that question means, but so CL, at least here for the curve we have for TechPod, it just continues here. I think maybe the last thing I just mentioned about post-stall lift curve is hopefully an answer to that question, that it normally will drop off a lot and then somehow kind of level out at some point, and then it gets a bit hard to say what happens depending on the aircraft geometry way beyond that point. But yes, so CL per angle of attack, at least beyond stall, it just drops off a lot. That's our big decrease in lift. So especially for this lecture, really all you need to know about this relationship is you have that linear region of lift with angle of attack in the nice place where you can fly, and once you hit stall, steep drop off of lift. So then last question I see in the chat here, is it still in stall? I think maybe I answered that already. You can tell me in the chat if not. So beyond the stall point, yes, it's still in stall. That's, I guess, just the definition here, because beyond this point we still have separated flow. So as soon as you have separated flow, you're in stall. This is the point to remember. I think that is the last part of the, yeah, so I have no more slides as far as this practice exam question is concerned. So this, hopefully it was a useful example for you. This is something very similar to what you might see on your own exam. So, you know, please go through if you have any other questions over the process of this part A, part B exam practice question. Feel free to post into Piazza, or also, I mean, so for another 15 or so minutes, if you want, feel free to just turn on your mic and ask me a question, or post in the chat for everybody. So I'm here for another 15 minutes or so. Okay, so from Jan, why does the headwind decrease the ground speed? Assume headwind would add up to relative wind velocity the airplane sees. So again, this is, so I'm glad if people post these questions, because it's good to clear these things up. So again, we've defined wind in this lecture for the whole fixed wing part of it as the movement of the entire air mass, and we're defining it as steady, which means it's not changing, it's not varying, there's no transient, there's no force effects on the plane. It's only a velocity component that adds up to that final ground speed. So the ground speed decreases when you have headwind, because basically, let's say you're flying and here's a box around where I'm flying, and this box is my air mass. So if the air mass is static, it's not moving, my ground speed is going to be the same as my air speed. As soon as that air mass is also moving, as I'm still flying inside of it, then relative to the ground, I'm going slower, right? Because I still have to, I'm flying at the same airspeed within that box of air, but that box of air is also moving me at some constant velocity in a different direction. So you sum the two, the airspeed vector and the wind speed vector are summed to get ground speed. So for headwind, since our wind, our box of air mass is shifting this way, if we wanted to maintain the same ground speed, we'd have to fly even faster than what we were before. So in this case, if the airspeed is the same, ground speed is less. Okay, I think that's also an easy way to think about it. Walking on a moving, yeah, that's a good one. So I'm sorry for pronouncing names wrong. Panagiotis says that an easy way to maybe think about it is that a passenger walking on a moving train. Yeah, totally. So yeah, so I guess if you were standing on the moving train, we can think of the train as that air mass that's moving over the ground. And so if we're standing still on the train, our ground speed then is the same as that train speed. But then if we start moving, let's say forward towards the front of the train, now we have a faster ground speed than before, because we have our, so wind speed in this case, the train speed, moving over the ground, plus our own speed relative to that train. That's actually just a very good example. So thanks, Panagiotis, for that example. It's a good one. From Aiden, would the headwind decrease VA? So no, at least how we define it here. So again, I keep making this distinction of steady wind, static wind, constant wind. And the reason I'm saying these words about the wind and how we have it defined in this lecture is because we're separating it from any kind of forces, aerodynamic forces acting on the plane. We're saying that we've already kind of settled out into a stable or a steady condition where the wind is only behaving, as far as we're concerned, as an extra velocity component relative to the ground. In reality, basically, how does wind actually interact with the plane. So as it's ramping up with the gust, for example, there will be some kind of force that's exerted, an aerodynamic force exerted on a plane. But as far as relative to our flight speed through the air mass, once that wind is kind of stable and we've already compensated for this additional force, it actually behaves really, really similarly just to a velocity component. So that's why we model it this way. Yeah, so again, really there's distinction here. So headwind, in this lecture, we define it as a velocity, not as a force. So it will not decrease the airspeed. It's only decreasing the ground speed. Okay, so another question. We always. So from Thomas, he says, in the equations, we always have to use ground speed. No, it depends on what's being asked. So, so specifically in this part B, if I go back up here, yes, so this relative to the ground point. So I specifically mentioned relative to the ground and italicized it because this is indicating that we're really talking about a curvature relative to the ground. And since it's relative to the ground, that's why we need to consider the ground speed. If we're talking about something like, I don't know, increasing angle of attack or just through the air mass having a different loiter. So let's say even if there is wind, but we're just not thinking about it and we just want to have a constant bank and turn at a constant air mass relative radius. So this isn't normally very useful in flight and practically, but if we wanted to do it, you would still use that airspeed in the equation here for the roll. So whether you use airspeed or ground speed in this roll equation or the other ones, it really depends on if you're talking about a radius that's relative to the ground or a radius that's relative to the air mass. Okay, so then next questions here. It's the chord of an airfoil. Aha, so this question actually is similar to one that's been asked on the Piazza already. So is the chord of an airfoil always aligned with the x-axis in the body frame? So it's a good question. So the answer, as I put in the Piazza, but I'll repeat it here, is no, it's not always aligned, but it's normally quite close. And the reason it's not always aligned is that, one, a lot of times wings, they don't have a constant incidence is what we call it. So basically, if I have an airfoil, let's say the chord is flat like this. The thing is, we could have something called geometric twist, which as we go further out on the wing, we start actually getting either more or less angle of attack for that chord line. And these have different stability properties depending on how the designer wants the plane to act. So that means we have different, basically, angles of attack for our chord for the same body axis. So then our definition, if we would say that the chord is always aligned with our body axis, it wouldn't be very good because we have different chords. So the other thing is you could just, even if it was a constant, so no geometric twist, but you have a constant chord line for your main wing, it's still very common even just to have an inherent incidence angle. So an inherent angle of attack at, away from the body axis for the wing. And again, this is just done depending on the designer or the performance specs of the aircraft. If maybe they know that that's the optimal angle of attack and they want their, for example, their fuselage, I don't know if they're like a scanning UAV or something, they want that fuselage in a specific orientation that's quite flat, but they want to have a more optimal for range or for endurance angle of attack of their wing, like in the general sense, they might put that incidence there. And so the definition for the X body axis, it's quite a loose thing actually. It's just saying out the nose basically is the loose definition for X body axis. And the reason it's loose is because it's hard to say, you know, if you take the main wing, you know, which chord on the main wing do you take? Is the, you know, there's also a tail. Sometimes you have other weird configurations of aircraft where maybe there's two wings. So it's, or two different wings. So that's why the general definition is kind of loose. It's just saying X body axis is generally out the nose of the aircraft. More specifically, where it might be defined for a small UAV, at least practically speaking with your autopilot, is just wherever the IMU is oriented. So generally, again, you try to orient the IMU such that the X body axis is out the nose of the plane because we want it kind of forward facing. But let's say what the autopilot would be concerned with is, okay, my IMU is telling me I'm oriented like this, and it doesn't make too much sense to try and put your IMU at a weird angle and then compensate it, because this is very hard to measure. So that's why I was saying it's loose. It's a bit of a loose definition, but just all you need to remember is out the nose is X body axis. It is normally quite close to being parallel with the airfoil of the wing. And then for the Y axis, out the right wing. So I think that's in the, I'm pretty sure that's in the pre-recorded lectures. So this definition. I think I've missed a couple now. Oh wow, lots of new questions. So is no, then in the semester exam. So another question here about an end of semester exam in December versus the session exam next year. So I don't believe there are any other midterms, for example. You'd need to ask Marco about this. I believe not. I think all the quizzes he's given so far are all you'll have, aside from now the final just session exam. So there's no quiz for the fixed wing part. It'll just be something like what you saw here with the practice exam question on the session exam next year. Then, okay, next question. So in part A, it wasn't relative to the ground then. Or, let me try to remember. So part A, so the question is in part about whether in part A we were considering things relative to the ground or not. So let's look. So part A, yeah, so I didn't specify relative to the ground, so then you can assume. So if ground relative is not specifically specified, just assume we're talking about through the air mass. So you could say, you know, VG equals VA, but you don't even need to say this. You could, if we're only talking about flight through an air mass, then it doesn't even matter what the wind is in our case, because the wind is just a velocity increment on the ground speed anyway. So basically, if you see the exam question and it doesn't specifically say we're talking about ground relative, like say turn radius, for example, then you can consider it's just using the air mass relative motion. Okay, then try to catch up with these questions. Sorry, guys. Elongation of the airfoil during landing. Aha. So this is from Jin Cheng. She says, okay, or he or she. I'm not sure with the name, but the question is, I often see the elongation of an airfoil during landing. So what is this doing? So that's actually an example of. So maybe if you were taking a flight, right, a commercial flight, on landing they will. You'll see they're actually flaps. So they're kind of coming out and they're going down. So if our airfoil is originally like this, and now we have kind of more surface area and a higher camber. So this is called camber when you have more of this kind of curvature on the airfoil. This generates more lift. So the whole idea there during landing is they want to make a lot more lift. They're also making more drag, which is normally okay for landing. So you want to kind of slow down anyway. But the main purpose of those flaps, and there's many different kinds of flaps that they could be using, but generally they're still called flaps. So they're extending the surface area. So if you remember the lift equation, where did it go here? Lift equation, yes, lift equation. So how do we make more lift? I mean, we only have a few options, right? The density near the ground is going to be constant. And then we have our angle of attack and surface area and speed. So as they, and our lift coefficient, but our lift coefficient is determined by the geometry of the airfoil. So if they're if they're changing the camber of that airfoil, they're changing this lift coefficient actually. So here we only considered angle of attack as a way to change the lift coefficient for a given airfoil, but you can also change the lift coefficient with your deflection of flaps. And then further for the elongation part, that increases our surface area. So then we again get a bump in lift. Okay, so then I really got to catch up on these questions. So how do we define angle of attack between chord and airflow, or between, so maybe another good question. So this was again answered in more detail on the Piazza, if you can find that question, but I'll quickly answer again here. So I think the confusion is coming from in the first video segment, 2D airfoil analysis was shown, where we were only looking at that cross section and we only had the airfoil itself to consider. So when you're only looking at a 2D airfoil analysis, the angle of attack is between the flow and the chord line. But for everything else, when we're talking about the full plane, we're summing everything and lumping it at the CG. So we don't consider the airfoil of the wing as our body axis. Sorry, the angle of attack is not from that airfoil of the wing chord line anymore. It's just from the body axis of the plane. So it's difference of full aircraft versus 2D airfoil analysis. So again, I'll just repeat just to make sure it's clear. 2D airfoil analysis, we're only looking at the airfoil, so angle of attack is from flow to chord line, but for the full aircraft, it's from flow to body axis. Okay. Next question here. So, okay, this question then, it's asking about, I think maybe a bit of confusion on the wind frame versus wind itself. So again, the wind frame is just this kind of, I guess I don't have the slide here, but it's just this definition of basically where the airflow or airspeed vector is pointing. So with we rotate through angle of attack and through slip to get to this wind frame axis. But this is not, and again, I put that big red note in the slides because it's important not to confuse this with inertially defined wind. So wind frame is still within the air mass. It's not considering our inertially defined wind. Yeah, so that's, I think, all I can really say about that. So it's the definitions in the slides from the pre-recorded lecture. But just remember, wind frame is not, it doesn't have anything to do with the inertially defined wind. Okay. Oh, I actually caught up. Okay, good. So why would we need more lift during landing? So yes, actually, thank you, Jan. That was one answer from Jan saying to reduce speed, or Mikkel, not sure which is the first name, but so yeah, the question was, why do we need more lift during landing? So reduction, you will kind of get a reduction in speed, not necessarily from the lift, more from the drag. basically more lift during landing is just a bit safer, right? So the main thing you actually do want to do is reduce speed for landing, but having more lift during landing also just gives you more options. Yeah, it's just a bit safer. I don't know if there's more to say about that. Okay. Yes, another point from Manuel, lower speed, shorter the runway needs to be. That's also a good reason to try and reduce your speed on landing. There's actually a class of vehicles called short takeoff and landing vehicles. And if you look at their design, you'll see super cambered, really big flaps. And yeah, and Simon Tobler says enough YouTube videos on. Yes, there's lots of nice YouTube videos on this. I encourage you to go look. A bunch of different kind of, actually they have competitions for these short takeoff and landing vehicles. And you'll see again that they have like these, you know, thick, wide wings, lots of surface area, and then like these huge flaps. And it's because they're just trying to generate a ton of lift, also a bunch of drag, and they come down like, I don't know, like a helicopter basically. It looks really weird. But it's cool because it gives them, it makes it to where they don't need a huge runway. Takes up space, infrastructure. It's actually something for fixed-wing UAVs that's, I say not, let's say, researched enough in my opinion in literature, but it's actually something we work on a bit in ASL, trying to make our planes land a bit shorter, because it is a problem if you don't have infrastructure and you don't have a bunch of space, and maybe there's some trees around, or I don't know, rocks that you don't want to land on. You only have this little patch of grass. Short takeoff and landing would be super, super useful. But that's also why these hybrid platforms, so convertible platforms that you'll hear about next week in the case study, are also super useful designs, and why people are using them a lot more often now, because they can take off and land vertically, and you don't need to worry about how do I, you know, generate a ton more lift, or you know, what kind of huge flaps do I need to have. So yeah, I guess if there's any other quick questions, maybe there's like 2 more minutes, but otherwise I guess we'd probably wrap up here pretty quick. So maybe I'll just give 30 more seconds or so for any last minute questions in the chat. Otherwise, if you forgot something or you think of something later that you want to know a bit more detail on, just post in the Piazza and I'll get around to answering it. Okay, so it looks like there's not too much else coming in the chat. So yeah, thanks for the attention, guys. I hope it was helpful, somewhat of a review, some more detail. Again, post in the Piazza if you have more questions, and please take a look at the, so later tonight we'll post the fixed-wing case studies. Please take a look at those videos. It's a super nice lecture from, so Sebastian Fairling, one of the co-founders of Wingtra. So the bright orange tail-sitter UAV you might have seen around the lab or around Zurich even. He has a really nice lecture actually on how do you model these things, what's the process, and why does it matter. And then after that, David and Michael their PhDs in ASL, they're going to talk about some of their own work on tilt rotors and tilt wing convertible aircraft. So super cool stuff. Please take a look at the videos. And yeah, so I guess see you later.